Okay, the next speaker is Adrien Moulinas. And please, the floor is yours.
Now you hear me again? No? It's working? You hear me?
Yes.
Yes? Okay. Good. So I'm a PhD student, and I also work with a company called Alice and Bob, which is a startup in Paris that aims to build a quantum computer based on CAD qubits. So I realize that most of you aren't really familiar with that field, so we spend a lot of time in my presentation discussing and trying to introduce this field. The goal of my presentation will be that at the end, you're able to understand what this graph means and why it is kind of impressive. So I will start with a short introduction to circuit QED, which is a field that Alice and Bob works in. So introducing how it works and how it interacts with the outside world. Then explaining why we need to have a bigger description than with the Schrödinger equation. So introducing the Lindblad master equation to represent the system. And how naive methods that try to do that scale poorly, and why we try to introduce a threefold compression method to actually be able to perform those kind of computations. And then we show two types of applications that we do with those methods. So circuit calculation is something in the field of circuit QED that gained a Nobel Prize yesterday, if you follow the news. So the idea basically is to take a circuit from electricity 101. So for example, here, just a coil, so an inductance and capacitance, put them together at very cold temperature. And then if you write the Hamiltonian of that system, then you will see that you will get quantized level of energy. So you can promote the phase and the charge in your system as quantum operators. And by writing those operators A and A dagger here, so which will create one excitation level, and A dagger which will remove one excitation level, or the opposite, sorry. A will remove an excitation level in your system, and A dagger will add an excitation level. And then you end up with an Hamiltonian with a very simple form for this system, which looks very much like an harmonic oscillator, like an harmonic oscillator. So like a physical cavity. That's why we call this field circuit quantum electrodynamics, because it's really close to a cavity electrodynamics that maybe you know about. So this only works under the assumption that your system is very well isolated from the outside world. So you have a very high quality factor. So basically your system is able to keep its energy for a long time, and you work at a very small temperature so that your system is superconducting, and as well, you are well below the gap of energy so that your system is dominated by quantum fluctuations and not by the thermal excitation. Yeah. So with the system that I just described, you were able to build an Hamiltonian whose energy levels are well separated, and they are separated by the same distance every time. So if you want to actually build a qubit with that, it will be kind of hard, because if you send a microwave pulse to your system, so you just send energy to your system, then you will excite all the transitions in your harmonic oscillator, and so you are not able to isolate the 0 and 1 state. So what you can do to prevent this is to replace your inductance by a Josephson junction to create some anharmonicity in the system, some nonlinearity, sorry, which will basically, as the first approximation, make it so that now your two first excited states have a difference of energy which is not the same as the other transition. So you are able to isolate this transition and to actually have a two-level system, an effective two-level system that you can access. This is what has been used for most applications to build qubits based on circuit QEDs. For example, the chip at Google, they use transmon qubits. But the bad thing is that since those qubits are not very stable, they have a lot of errors. So here with these qubits, we have two types of error. We have bit flip, but we also have phase flip, which will take if you have a start in superposition of 0 and 1, you will go in superposition of 0 and sorry, you start in superposition of 0 plus 1, you will go to 0 minus 1. This is a phase flip. So you need to mitigate those errors by using redundancy. So basically, since you have two types of error, you need to mitigate them with surface code. So one dimension, you correct for one type of error, and the other direction, you correct for the other type of error. But so this comes from the fact that quantum states are fragile. So if you think back to the Schrödinger cat experiment, then your cat is in a superposition of dead and alive, and the third experiment assumes that the measurement and the interaction with the outside world only happens once you actually measure your system. But a lot of things can go wrong before that. For example, it can emit light differently depending on the state of whether the cat is dead or alive. So the cat can make noise, or it can vibrate, which will actually destroy the superposition in your system. So this is kind of paradoxical in quantum computing, is that you want to have a system that is as much isolated as possible, so that you can preserve the information in it, but you want actually to be able to access it. Otherwise, you cannot do anything with it. But by adding some kind of control, then you introduce spurious noise. And so, yeah, so basically, if you want to be able to control your system, then you will create errors, basically. But what if you were able to use this kind of noise, this kind of interaction with the outside world, to actually stabilize your system? So there is a way to do that with a mechanical oscillator, to use actually dissipation as a stabilization process. So if you take a mechanical oscillator with here a spring and a damping parameter and a damping system here, and you excite the top here, then your pendulum here will start getting excited, and thanks to the damping, the excitation will remain contained. And so dissipation prevents the motion from diverging. And from a symmetry of a problem, if you write the actual equations with classical mechanics, you see that two possible solutions will appear in which you can encode information. You can say that basically we'll have oscillations at the same frequency, but with a phase 0 or pi. And you can say that your system with a phase 0 is your 0 logical, and phase pi is your 1 logical. So those two solutions are stable steady state. So if you start in whatever state, you will end up in one of those two ones. So either in 0 or pi phase. So dissipation really stabilizes the system in that case. You actually use the dissipation, the connection with the outside world, to have a stabilized system. And this works. This is compatible with quantum computing because in that case, the environment is completely oblivious to the phase of your system. So meaning that if you just hide this part, then for the environment, which is represented here by this oscillator, by this system, sorry, then it is completely oblivious to what the state of the system below it. So this kind of stabilization is compatible with quantum superposition, and the key ingredient, if you want the equation, is that the dissipation here will be sensitive to phi squared. So if you are in 0 or pi, then phi squared will be the same. Okay, and so at Adrien Moulinas, some people actually built this mechanical oscillator. So if you start from a non-excited state and you start exciting it, so this is basically what I presented earlier, but with an actual implementation. And then here on the video, they superpose multiple experiments, and you see that in all the time you will end up in one of the two systems, so either with a phase 0 or pi. Okay, so here we are able to do some kind of superposition by just superposing multiple videos together. But in practice, you only get one of the oscillation. And this is resilient to what we call bit flip. So in that case, it's just perturbating your system. Because even if you perturbate it, it will just go back to the same system as before. But if you perturbate it too much, it can happen that you will get a bit flip, so meaning that it will go to the other phase, so 0 to pi or pi to 0. Okay, so this is for the physical oscillator, but how do you actually do that in CP3D, or do you actually make it quantum? So what you can do with a superconducting cavity is that you can build easily what we call a current state in it. So a current state is the most simple state that you can create in a superconducting cavity. Is you just add a drive to your cavity. So you send photons at the resonant frequency of your cavity. Here I wrote the equations in the rotating frame, so there is no longer the first term of the equation I presented earlier. And since your cavity, of course, is always coupled to the outside world, then it will lose photons. So we call them photons, but in reality, it's just excitations. We just go down the excitation ladder, but we can also call it photons by analogy with 3D cavity case. And so if you write the equation for this, you see that you will, in that case, you are able to stabilize a current state. So with the dissipation, you stabilize a current state of amplitude alpha. So here I represent what we call the Wigner function of the state, which is basically just a way to represent a wave function or a wave function or a density matrix in the complex plane. So here you get basically a Gaussian distribution centered on the point alpha. But this is not very good to do actual computation with this because this is just a single state that you stabilize, but you would like to stabilize a two-level system. So to have two systems that are stabilized by your system, by your dynamics, sorry. And so the way that you do that, as in the classic case, is that you, instead of gaining or losing energy level one by one, you have to create somehow a way to gain excitations by pair and lose them by pair as well. And if you do so, you will see that you will be able to stabilize two states, plus alpha and minus alpha, that are stable equilibrium of your dynamic. So then with this is very good because then you can say that your zero logical is alpha and one logical is minus alpha. And then you see that if you start in a state which is closed, so here it's in the Wigner space, but it's actually you can think of it as just systems that are closed in practice with wave function, which has an overlap. If they start closely, so if you start in a state that is close with to minus alpha, you will go back to minus alpha. If you start in a state which is close to plus alpha, you will go back to alpha. And if you start, like in the video before, in the middle, so in an empty cavity, basically, then you will have actual quantum superposition. So you end up with a state with superposition. And here, the way that you can see with the Wigner function that you have a quantum thing happening is that you have your Wigner function becomes negative. So the blue here means that your Wigner function is negative, which is a trace of quantumness. Okay, but why do we bother making all this? So the idea is that when you build your CAD qubit, you have a control over this alpha here because I presented here. So alpha is just given by the square root of the drive over the dissipation. So if you drive more strongly, you will be able to stabilize a state with a larger alpha. So basically something further from the axis here, on the x-axis. Sorry. And by doing so, you see that the probability of bit flips occurring in your system will decrease exponentially with the size of with alpha. And the way that you can see that is that if you write the semi-classical equations, basically an approximation with of the dynamic of the system, but with just a single differential equation on alpha, then you will see that to go from alpha to minus alpha, you will need to jump over this bridge, and this grows exponentially with alpha. So basically, if you increase the size of your CAD qubit, so if you got a CAD qubit, then you can basically forget about one type of error. You are completely protected against bit flip because the probability of one occurring is much smaller than the probability of the other type of error occurring. So this was proven in practice a few years ago, so 5 years ago by Raphaël Lescan, then a few years after by Sébastien Jouzouin and other people. And the important thing here is to see that you plot the bit flip time, so the time it takes from you to go for your state to go to 0 or 1, so the bit flip occurs, against the number of photons. The number of photons is given by it's alpha squared, so it's proportional to alpha, but it's alpha squared. Then you see that as you increase the number of photons, you increase alpha, then you increase exponentially your bit flip time, and you are able to reach microscopic bit flip time. For example, here 100 seconds. Okay. So this is good because you have something that is very stable. But how do you actually simulate the system? Okay. So to simulate the system, you need to use something called the Lindblad equation, which is basically an equation that generalizes the Schrödinger equation to open systems. So where you need to take into account the interaction with the outside world. So instead of describing your system with a wave function here, then you take into account the bath around it, and you describe your system with a matrix now. So instead of having a system of size, for example, D, once you truncate, you have something of the size of D by D. This approximation is valid under the assumption that you have a Markovian environment, meaning that once you lose information to the bath, you cannot gain it back anymore. You lose energy to the bath, but the bath just absorbs it, and the state of the bath doesn't depend on the state of the system. And you have a weak coupling with the outside world, meaning that you lose energy and information to the outside world, but not too much. You're not too much entangled with it. Okay, so sorry, maybe to go back. So the form of the Lindblad equation is just the Hamiltonian that you had before. So if you just have this part here, it's just like the Schrödinger equation, but with a matrix instead of a wave function. But then you need to take into account the dissipation operators that I presented earlier. So for example, losing 1 photon, losing 2 photons at a time. Okay, so here in the first part, I present this reduced model to have a cat qubit in a cavity. But in practice, to engineer this kind of dissipation, it's not very natural to lose pairs of photons at once. So you need to couple your cat cavity with a buffer, which was something we call a buffer cavity, with which it will exchange pair of photons. And this buffer cavity is very lossy, so it loses energy to the environment at a rate kappa b, and you drive this cavity at a rate you drive this cavity with a drive of strength epsilon d. And so once again, if you write the Lindblad equation for this, you see that you will stabilize 2 coherent states of amplitude alpha square, which is minus epsilon d over d2. Okay, so that we know what we want to simulate. How do we actually do that? So instead of having a wave function, we have a wave function for the system, but we cannot simulate that because it's a Bodini system, so it has a support on an infinite sizable space, but you need to do some actual truncation. So for example, here when you simulate cat qubit, you know that the distribution on the Fock space will be centered around alpha squared. So you only need to take into account the 3 alpha squared first state to have an accurate description of the system. So you do a truncation there. But now, since you have an open system, you need to describe it with a density matrix. So you go to the density matrix. And if you want to couple multiple Bosnian systems together, then if you want to do the evolution with that, since doing the evolution means basically doing a matrix multiplication a lot of time, then naive evolution method, which will scale as d to the 3n because of the curse of the dimensionality. And so simulating, for example, a control node gate, so just a gate between 3 qubits, 3 cat qubits, is already challenging. It's already something that is very hard to do in practice. So what is usually done is that depending on the size of the system that you want to simulate, you do more and more approximation. If you want to simulate a single cat qubit, then you can really take into account the full system. As you increase the complexity, the number of bosons or of cat qubits that you want to simulate, then you need to do more and more approximation. So for example, if you want to be able to simulate 16 cat qubits coupled together, then you cannot, of course, describe the whole Hilbert space. So you need to use MPF methods. Okay, so now we'll start talking about actual tensor train. So I will explain to you how we can build basically an efficient presentation of the density matrix by making some assumptions on the state of the system. So the first axis that we can use is the purity approximation. So it's a method known in the literature as ensemble truncation method. What it means is that instead of working with the density, you know that your density matrix won't be of full rank. So for example, usually what is done is that you start in a pure state. So you start with just psi. So here you start with just a density matrix which is just of rank 1, so a single state. And even during the evolution, the purity of your matrix, so you can understand it as the rank will remain quite low. So for example, here, I do a simulation of X gate for a cat qubit. So X gate means exchanging 0 and 1. That's why you see the 0 moves to there and the 1 moves to there. And then I do an SVD of the density matrix basically at all time, and you see that the rank of your matrix never go above 10 for Hilbert space size of size 100. So basically, you can reduce by 10 the size of your system. And the intuition is a system of interest for actual applications of quantum computing will always satisfy the property. If you enter in a regime where your state becomes very complex, very impure, so for example, in the Wigner representation, you will have something with a lot of blobs everywhere. Here, then this is something that you want to avoid usually. So yeah, so in practice, you will often this hypothesis will remain true. The second hypothesis is the basis of MPS of matrix product state is that you suppose that your different botonic systems won't interact much. For example, if you think about coupling just multiple cat qubits together, then the only information that they should exchange between them is the state of the logical qubit, so if they are in 0 or 1, and not the state of the full Hilbert space. So basically, if you in your MPS, if you write it like this, then the information in the system should grow as 2 to the n instead of d to the n. So we just exchange information whether you are in 0 or 1 for each state. And if you think back to the buffer cavity cat I presented earlier, in the physical case, I explained to you that the way that it works is that the environment is oblivious to the state of the system of the system. So this means that basically you have almost no exchange of information between, for example, here the buffer cavity and the cat qubit cavity. So yeah, so what you can do is that you start from you take this tensor here, and you can do a low entanglement decomposition to build basically an MPS. And so what I forgot to say earlier is that in practice, when you do the computation, you never need to store this psi dagger in memory because you know that it will just be like psi. So you can rebuild it on demand when you need it, but you don't need to keep it in memory. And the last approximation that we do is we use Quantics to describe each Hilbert space. So here's something that is kind of different from usual Quantics representation that I don't need to introduce because everybody did it already, is that instead of discretizing a continuous function, we discretize a discrete function, but it works just as well. So you have a Hilbert space of size 2 to the n, so with states that go from 0 to 2 to the n minus 1, and then you write it as an MPS of n of a tensor train, of n tensors. So here I work in the Fock basis, and in this basis, everything works kind of well because when you build your MPOs, you see that they are often of the form, the operators that I presented earlier are often of the form an initiation operator times a creation operator, for instance, and those are Venn diagonal operators, so they are easily constructed with a TCI and with a low rank. So for example, the annihilation operator here, A, is of rank 6 for whatever side of your Hilbert space. And similarly, the state of the system, so your MPS, will be close to Gaussian state usually, because this is a Poissonian distribution of the state, which is very close to a Gaussian distribution. And those as well can easily be compressed with TCI. So usually you end up with a bond dimension of chi, which is smaller than 10. Okay, so just to sum it up, you started with a density matrix of, for example, here 3 bosonic systems coupled together. You do purification to write a system like this. Then you assume low entanglement between the different parts of your system to write it as an MPS like this. And then you do Quantics decomposition on each local Hilbert space to end up with a system that is like this. And so now to do the actual evolution, the Lindblad evolution in this format, sorry. What we do is that we use standard methods that were developed outside of the scope of tensor trains, but that can be easily applied to tensor trains. Because basically what you only need to do a matrix state multiplication or matrix multiplication, which will just be MPU contraction and MPU MPS contraction, which is easy to implement. Yeah. So the core idea of that method is that you write your equation, so your evolution process, so that takes you from row n to row n plus 1, so next step, as a sum of cross operators. So it's a sum of operators that you need to apply to the left and to the right of your density matrix to make it evolve. And the nice thing is that in the presentation that we've chosen, and applying this thing to the density matrix means just applying this K MPO to your representation of the density matrix. So it works quite well. So yeah. So what you need to do actually to do the evolution is that you apply the Hamiltonian evolution of your. You take a scheme, so for example here of order 2, you apply the Hamiltonian evolution by doing this kind of MPO and PS contraction. You apply the jump processes, which will be this part here, by using the same method. Then you sum everything together. So this is where you will increase, because you see here that you have an MPS with an extra leg here that represents the impurity of the system, basically. So as mu grows, it means that you have more and more. As mu increases, it means that you have a state which is less and less pure. So when you do the sum of different this sum here, sorry, then you will end up increasing this mu, and so you need to do purification to purify the state to reduce mu. And you can use the same step for higher order schemes. And for time-independent problem, you can even do something smarter, meaning that you can build this K operator directly as an MPO with an extra leg here of size L, which is the same as the number of terms in your sum, that you just apply repeatedly to your system until you reach the desired time. So now we just focus on two applications that we do with this presentation. So we do what I presented in the first slide of the presentation, what we call a Z-gate. So a Z-gate will take you around, will take you from the superposition of alpha minus alpha to alpha plus minus alpha. So it will take you from this state to this state. So the way that you do that is pretty straightforward. For a cat qubit, you add a drive, so the same form as I presented earlier, to your cat qubit, and this will naturally build this logical gate. And when you do this operation, you have a theoretical formula that gives you the error that you get during your process. And so here on the left plot, I show that as I increase alpha squared, so I increase the population of my cat, and I also increase, of course, the size of my system to match the size of the size of the cat. Then I see that I get the errors that match exactly what you would expect with the theory. And more importantly, if you look at the time it takes to do the simulation, depending on the system size, you see that if you do it with a naive scheme, then the simulation time will increase at the power law of the system size. And so here, since the x-axis is in log scale, you will just see an exponential. So at some point, if you increase the system size, your simulation time will just explode and you cannot do anything anymore. But here, since in this representation, multiplying by 2 the size of the Hilbert space means just adding one more tensor, you have a log scaling of the simulation time with the system size. So here, you see that you can simulate systems with quite big in reasonable time. Of course, you don't gain anything if your system is quite small, because just the overhead of doing your representation will be too bad. Okay. And here, I also compare it with a GPU accelerated library, so a library that uses it's supposed to be quite fast because it uses GPUs to compute the evolution. And so I get, as before, I get the same, basically the errors that I get match exactly the theory, so the results are correct. But the simulation time, you see that for dynamics, which is this library that uses GPUs, the simulation time that increases at the power law, of the system size. Whereas with our method, we can have a much better scaling, so meaning that we get a crossover here, where our method becomes actually faster. And if you go to an even bigger Hilbert space size, you will see that here you can continue going, whereas this becomes impossible to simulate. No, my method is on TPU. Yeah. Exactly. Dynamics is on GPU. So if I were to put this on GPU, then what we would expect to just have the same shape of the curve, but just below. Okay, and finally, the other problem that we looked at is something called Treisman ionization, which is a problem that was basically built to be hard to simulate with the classical method. So the idea is that you have a Treisman qubit, so from what I presented earlier, coupled to a cavity, so LC circuits, quantum harmonic oscillator. And you add a drive, so this is this line here, to the cavity, a very strong drive, which is detuned can be detuned from the frequency of your cavity. And by driving very strongly, you will excite a lot of states within your cavity and in your transmon. So to actually be able to simulate this, you need to have very large hyperspace sizes. So for example, in their papers, I took for the cavity more than 1,000 states, and for the transmon 32 states. Sorry. So the density matrix contains a billion elements. And so they argue that to simulate this, they needed to use what is known as the tensor processing unit, which are basically more powerful GPUs made by Google. They're even more powerful than usual GPUs. But we were able to replicate their result by using a single CPU, just using a laptop or just a computer, or a CPU. And so here, you see that what is interesting to look at is that you start in either the 0 or 1 state for your transmon and with an empty cavity. And then you start this process, so this evolution. And you see that if you start in 0, then you will go along this line here. So basically what will happen is that you will just stay in a state in the population for your transmon, which is close to 0, up until you have a population for your resonator, which is very large. But if you start in a 1 state for your transmon, and then as you populate your resonator here, then at some point you will have a crossover, meaning that you will end up with a very high population for your transmon. This effect occurs because of crossing with higher energy states. That's why when you do the simulation, even though you only look at states starting for your transmon 0 or 1, you need to actually take a hyperspace size of 32, for instance, because those effects happen because of those higher energy states. And so when you do the simulation by using the threefold compression method, you see that if you start in 0 or 1, you get a very much different behavior. So if you start in 0, then basically not very much happens. You get a system where the purity remains quite high, so close to 1. The population in your transmon remains close to 0, just as you increase the population in your resonator. And the mu p here, so the mu p that can be linked to the purity. So basically, if your purity is low, then mu p will be high, remains quite small. Whereas if you start in 1, then you see that your purity drops at some point because of this crossing here. That you can also see in the population here. You see that the population increases very much at some point. And then you will need to have a very large mu to be able to describe your state. Okay, so these kind of things show that, of course, transmon ionization is something that you never want to occur in your system, because here you would like, since you simulate a transmon qubit, you would like for it to stay in the state 0 and 1. So this kind of thing you really want to avoid, and this you can see that this process that you want to avoid will lead to a very high mu, so it will make your state less compressible. So this goes to show again that to simulate things that we actually want to work with, so for example, a well-behaved transmon qubit, then this threefold compression method can be actually effective. Okay. And so to conclude, here in the presentation, I showed that the open many-body bosonic systems are very hard to simulate with the usual method due to the curse of dimensionality. We are able to build this threefold compression method that exploits the expected behavior of the system and show that this and that can simulate different circuit QED systems, or a CAD qubit or a transmon. The current implementation that we built is limited to 2 boson simulation, because basically when you see this shape here of your tensor, it looks just like an MPS, where you just shifted the leg instead of putting it back, you put it up. But the goal now is to simulate more than a system with 3 bosons or more by using 3 tensor networks. So use 3 TCI to build the operators and the state, and then do the evolution in this manifold. So thank you for your attention.
Thank you very much. Questions? So I have a question concerning the purification process.
Yeah.
Is it just recompression, in fact?
Yeah. So what we just do in practice is that we just rebuild the tensor and then do an SVD. But there are also works that try to do that smartly. For example, by Tumaeran, to find since you have gauge freedom, because you see here you could add U, and so that when you actually rebuild your state, if you have U dagger on the opposite side, it will not change anything. So this means that you can add U.
Like a unitary transformation.
Sorry.
Unitary transformation.
Yeah, unitary transformation. Unitary transformation. And you could show this smartly so that it could reduce this mu. So this could be implemented, but we didn't do it yet.
It's like something like using symmetries, right, in the construction of the tensor. Okay.
Yeah.
What I didn't get from thanks for the talk, but what I didn't get is how much you deviate from a semi-classical state from the cavity to some extent. Because if I was just changing bases, and I would just work in a basis where I just look at superposition of classical state, would I then also have, wouldn't I be more efficient? Because if I got it right, you work in the Fock space, so.
But if you want to compare this to semi-classical approximation?
Yeah, so I can just write my ansatz as a superposition of semi-classical state of the cavity as broad, so.
No, but this is just, what I presented here was just a way to look at it, but in practice, you will get something that is more complex than just a superposition of current states.
But can you quantify that? Meaning, did you check how much you deviate from this state?
Yeah. Well, for the cat qubit case, I don't have figures here, but yeah, I just show that if you do once you get your state, you just compute the value of alpha, and then you compare this to a current state of size alpha, and you see the overlap. See what I mean?
Yeah, a single state, a single coherent state, or a superposition of coherent states?
You have a superposition of coherent states. For example, this simulation here, you cannot do with just a single with semi-classical approximation. No.
Okay, but
because
we
it's
discuss this, but
yeah, we can discuss
I can improve this approximation systematically to some extent.
Okay.
Okay.
No, so sorry about also. I'm curious about this semi-classical. I mean, you can use a base of coherent state. You can represent any density matrix that you want, and the semi-classical will tell you that it's just this coefficient would just be picked at some. You just have one coefficient, then it means it's semi-classical. So, to me, how much you are far from semi-classical is how much coefficient you would need to represent this state with respect to. I mean.
Yeah, I see what you mean. But basically, when you do the evolution here, at first, of course, you start with a single coherent state. But here, you won't end up necessarily with a superposition of coherent states. You'll end up with something that you cannot really.
Okay, so basically, if you try to use a basis of coherent state to build, and your tensor train is the coefficient of this coherent state, basically the one dimension will grow. Or
actually, I haven't checked, but this is what maybe we wanted to do at some point, is because here we work in the Fock space basis, but this could be out of interest as well to try different bases. You're right.
Okay.
This we haven't really done.
Okay, thank you.
Your last slide on the outlook.
Yeah.
You had this comb. On the last slide of the outlook, of this comb structure with, if I understand correctly, the discrete bosonic space for each of your, let's say, it's represented.
Yeah.
Like in a Quantics representation. So I really like this idea. How far have you pushed this, or have you not implemented?
Not yet. Actually, that's the goal to do it now. We have not tried it yet, but we have hope that it will work well.
Yeah, okay.
But no results yet.